it's made. Firefighter boots. What's hot in footwear? Garden tools. You'll get the facts in spades. Automated machines, our annual tribute to those moving marvels. And gypsum board. We're giving this story wall-to-wall coverage. Firefighters need boots they can pull on lightning fast to get to the blaze as quickly as possible. Those boots have to be fire-resistant, of course, and waterproof. They have to provide good grip for climbing ladders and be sturdy enough not to puncture when stepping through sharp debris. Firefighter boots start out as a chunky block of rubber. The first step is to put the block through a mill. It passes through the rollers over and over again until it gradually flattens and thins out. Workers then add chemicals, anywhere from 15 to 35 different types, depending on the model of boot they're making. The rubber formulation is what makes the boot fire-resistant. Once the rubber is smooth and malleable, about the consistency of modeling dough, they form it into sheets from which they'll cut the various pieces that make up the boot. They feed this sheet through rollers that imprint vertical lines on the rubber. They'll cut the sheet along these lines to make the strips that run down the back of the boot. From another sheet of rubber, using a handheld die, they cut one layer of the multi-layered sole. They run an extra thick sheet of rubber through rollers that imprint a tread pattern. Then workers cut out the bottom soles. They mark the boot size on the bottom. Using yellow rubber, they cut out the boot's toe cap covers. The boot's leg has a stiff lining to prevent it from wobbling. Workers cut it from a rubber-backed cotton fabric following a pattern. Once all the pieces are cut, workers can assemble the boot on a form. They start with the lining, wrapping it around the front and gluing it closed at the back. Then they glue on the insole. For this model, it's made of rubber-backed felt. They secure the lining seam and seal it with one of those rubber strips we saw earlier. Now, the vamp, a piece of felt reinforced with a thin layer of rubber. This gives the boot strength. Next, the toe cap sponge, made of rubber compounds. When they cure the boot, the sponge will inflate and hold this steel toe cap in place. To protect the firefighter's feet when walking through sharp debris, a steel arch and a steel sole. Next, an adhesive-backed toe cap cover. Then a felt sole to protect the firefighter's foot against heat. It has a steel arch for stability when the firefighter climbs the ladder. After applying a rubber heel reinforcement, they cover the lower part of the boot with yellow foam for insulation. They secure it using a strip of rubber. Now they finish the bottom of the boot in black rubber. They reinforce the back and sides in yellow rubber. And finish them off in black rubber. Next comes the yellow toe cap. Then a rubber pad to protect the front of the boot when it rubs against the rungs of the fire ladder. Now the bottom sole. They use a press to seal it in place. Rubber bonds to rubber under pressure. They apply a rubber trim around the bottom, using a small roller to press it in place. Workers then press all the seams to ensure they're well adhered. Then it's into a vacuum machine for about 4 seconds to create an airtight bond. Finally, the boots go into a giant oven that heats them to 140 degrees Celsius. An hour and 45 minutes later, the rubber is cured and hardened, and all the pieces have fused together. These boots are ready to take the heat. Anyone with a green thumb knows that it takes both skill and patience to make a garden flourish. It also helps to have the proper tools on hand. An avid gardener's arsenal can contain everything from shears, trimmers, and pruners to rakes, hoes, and spades. The handles of these garden tools are made of white ash, a sturdy wood that can withstand the force of shoveling, digging, or raking. These dried ash dowels measure 0.5 meter to 2 meters long, depending on the tool being made. They first enter what's called the chucking line, where specially designed automated machines shape them into handles. The first operation rounds the dowels to the required diameter, 4 centimeters or so, depending on the tool. The next operation cuts the dowels to the required length and profiles their ends. Two chucking heads, one on each side, carve the ends simultaneously. One shapes the bottom of the handle to fit the tool's blade. Certain blades go over the wooden handle while others go into it. For those inserted blades, another chucking head hollows out the handle. Meanwhile, the chucking head on the other side rounds off the top of the handle. The finished handles spin against a sanding belt as they exit the chucking line. This smooths the surface of the wood, preparing the handles for a coat of protective varnish. High-end shovels and spades have what's called a steel D-grip, a steel handle grip with a wooden insert. An automated lathe first shapes a piece of ash to the right length and profile. Then an automated drill pierces a hole. To make the sides of the grip, workers begin with 2 pre-cut pieces of steel called blanks. They place them in a manually operated press that shapes them in a 2-step process. They use the heat of a strong electrical current to melt the steel and fuse the pieces together. This is called resistance welding. Next, they feed a steel rivet through the sides and wooden insert and fasten everything together. Elsewhere in the factory, meanwhile, a heated forming machine stamps out the steel blanks that workers will shape into blades. A robotic arm loads the blanks into an oven. In a mere 4 minutes, the oven heats the steel to almost 1,000 degrees Celsius. This intense heat makes the metal malleable. Workers then take out and shape one blank at a time. They have just a few seconds to form the steel before it cools off. The first press forms the blade, in this case a shovel, and a partial socket. Then the second press closes the socket. They quickly submerge the blade in lukewarm water to cool the metal down. By now, the steel is extremely brittle, so the blades go into what's called a tempering furnace for 15 minutes. This alters the metal's internal structure, restoring its strength. The steel D-grip, meanwhile, has been cleaned and painted. Workers insert the wooden handle and nail the parts together. On the other end, they attach the blade, which by now has been varnished to prevent corrosion. After drilling a hole through both the metal and the wood, they fasten the blade using a rivet if it's a high-end tool, a nail if it's a budget model. These hot-off-the-press garden tools are finally ready to put in a hard day's work. A couple of centuries after the Industrial Revolution, mass production met automation, a match made not in heaven, but in high technology. In this special segment, How It's Made honors the automated machine with this moving tribute. It's called gypsum board or drywall, and chances are your walls and ceilings are made of it. Years ago, it replaced plaster as the wall material of choice. Workers just mount the sheets onto wood framing, plaster the joints, then sand and paint. Gypsum is a natural mineral. Since ancient times, it's been mined to produce gypsum plaster. In fact, there's gypsum plaster in Egypt's pyramids. In 1894, a man by the name of Augustine Sackett patented a board made of gypsum which he called plasterboard. But it didn't become the norm in construction until the building boom that followed World War II, when busy contractors abandoned plaster in favor of this faster and cheaper way to build walls. The process of making gypsum board begins at the quarry, where crews mine the gypsum, a soft rock. The loaders dump their haul into what's called an apron. The apron channels the gypsum onto a conveyor, breaking up the big chunks along the way. From there, it's into a giant rotating drum. Within 8 minutes, this hot air rock dryer removes 5 to 10% of the moisture, turning the gypsum white. Next stop, a gas-fired silo called a kettle. It cooks the gypsum at 150 degrees Celsius until most of the remaining moisture evaporates. Feeding that kettle, a mill that grinds the lumpy rock into what's called stucco, a fine powder the consistency of wheat flour. In a mixing tank, meanwhile, workers combine water with several powdered chemicals and minerals, and a chemical soap. The dry additives give the board the required structure, while the soap creates air bubbles to make the board lighter. In a separate machine, they mix the stucco with an accelerator to make the gypsum set faster. Now they combine the two separate batches, creating a mixture called a slurry. It looks like thick white soup. Now they'll form it into gypsum board, which is basically a slurry sandwich. The bread is this thick, heavyweight paper. As the roll unwinds, creaser wheels, as they're called, score a line about 3 centimeters in from both edges. Then a machine evenly spreads the slurry, like a sandwich filling, between the top and bottom sheets of paper. Then the paper folding operation, most of which is a company secret and off limits to our cameras. They fold the edges along the score lines, the bottom edges upward, the top ones downward, gluing them over the bottom ones to trap the slurry inside. Drops of water smooth out any ridges, ensuring a smooth and even fold. Forming plates then shape the folded edges into straight sides. An optical sensor checks the depth of the board's recess. That's where you put the joint tape to connect one board to the next when you're building a wall. The forming station spews out 305 continuous meters of gypsum board at a time. A cutter now chops that mega board into whatever length board they're producing in this run. As the boards exit the cutter, automated prongs flip them recess side up. Since the recess side will be the wall surface, they don't want to risk damage by having it travel face down on the rollers that lead to the drying station. This gas-fired hot air dryer is kind of like a multi-level parking garage. It's more than 150 meters long and has 8 decks. The factory can cure hundreds of boards at a time. It takes 40 minutes to move through the dryer's 4 temperature zones, which start at 350 degrees Celsius and get progressively cooler to 150 degrees. The boards are sold in pairs, so the machinery stacks them in twos, then tapes them together. The tape bears the brand name as well as the size and thickness of the board. Standard lengths range from 8 to 14 feet. and the most common thicknesses are 1/2 inch and 5/8 of an inch. In this industry, imperial measurements are still the norm. The tape also tells the consumer what type of gypsum board it is. There's standard drywall for building walls in homes. There's a moisture-resistant version for humid areas such as bathrooms. There's also fire-resistant gypsum board, usually required by law for commercial buildings.
Wood-burning stoves. We're getting all fired up to bring you this story. Orthoses. Brace yourself for an inside look at these limb supports. Ballet slippers. The whole song and dance. And buses. We'll check out every stop on the production line. Wood-burning stoves do more than create a cozy ambiance. They're also powerful enough to heat an entire house. More and more people are installing a wood stove as an additional heat source in their home. It's economical, and the new low-emission models are more environmentally friendly. Every wood stove has a fire baffle, a stainless steel barrier above the burning wood that shields the top from the intense heat. The baffle also slows down the smoke exiting by the chimney, which reduces the upward draft that the rising heat creates. Production begins with large steel sheets that are 8 millimeters thick. A computer-guided laser cuts out pieces that workers will shape into the various parts of the stove. The laser slices through the metal quickly and with extreme precision. And because it cuts with intense light rather than punching force, the pieces have neat, smooth edges. Workers use a strong magnet to lift and transfer the pieces to the next production area. The largest piece becomes the surround, the part that forms the sides and back of the wood stove. Workers use a machine called a press brake to shape it. A computer guides this large hydraulic press to bend the flat steel in exactly the right spots. Now they position the surround in an assembly jig to keep it steady during welding. After welding the front of the stove to the surround, they weld the air intake, which allows oxygen to enter the stove and feed the fire. Next, they weld the top, the fire baffle, and air channels near the top, which are also designed to feed the fire with oxygen. The quality of welding in a wood stove is critical because the joints have to be able to withstand extreme heat. Now they weld the bottom of the stove. It has a hole in the middle through which you sweep the embers to an ash pan below. Now they weld the flue collar, the steel ring that attaches the stove to the flue pipe that leads to the chimney. Workers now bolt the stove to a pedestal. The pedestal is also made of welded steel. Meanwhile, the door takes shape. They glue a fiberglass rope to the perimeter of the door frame using a silicone-based glue that's resistant to extreme temperatures. This cord prevents air from seeping in through the door and fueling the fire out of control. After installing the locking door handle, they weld the door hinges. The stove's interior, where the wood burns, is known as the combustion chamber. They line it with bricks to protect the walls from warping in the intense heat. Bricks do deteriorate over time, but it's easy to replace them. The last steel part they install is the cap for the ash pan. Now an automated conveyor transfers the stove to the paint station, where a robotic arm sprays on a coat of heat-resistant paint. Once the paint air dries, a worker removes the door to install its glass panel. This isn't your run-of-the-mill window glass. It contains ceramic, which enables it to withstand temperatures up to 1090 degrees Celsius. With the glass panel in place, workers can apply decorative features and information stickers. Then, they put the door back on and lock it shut. They rivet on the company logo. Then, install a fan in the back. The fan blows out the heat that the stove generates. When the wood-burning stove leaves the factory, its coat of paint is dry but not yet cured. The heat cures it when you fire up your stove for the first time. Orthoses are devices such as arch supports and braces that address a joint or muscle problem in the back or extremities. An orthosis can provide artificial support, prevent or correct a deformity, or improve how a weak or painful area functions. You can buy an orthosis off the shelf or have one custom made. Producing a custom-made orthosis starts with a thorough examination. A certified professional, called an orthotist, analyzes the problem area. In the case of this patient, the feet. After a few manual manipulations to test the range of motion and pinpoint weakness or pain, the orthotist uses various instruments to measure the angles of the different parts of the feet. Then, it's on to specialized devices that analyze foot position and movement during standing and walking, and how body weight is distributed onto the feet. In this scan, the red areas show that more weight is landing on the left foot than on the right. Next, a 3D impression in foam. It goes to the production department, where technicians fill it with plaster. Once it dries, they extract an exact model of both feet. Now they can construct the orthosis piece by piece. Most of the components are made of different types of polyurethane, a lightweight thermoplastic. Each type is designed to produce a specific effect at a different phase of the patient's footstep. For example, the blue base is made of rigid polyurethane that holds the foot in the correct position. At the front, dense black polyurethane helps propulsion and reduces stress on that side of the foot. They cover the assembled orthosis with a sheet of glue and put it into a vacuum press. The press applies heat to activate the adhesive. It sucks out the air between the components and compresses them tightly together. When the orthosis comes out, they place it on the model of the corresponding foot. Then it goes into a different vacuum press to mold it to the shape. They add made-to-measure corrective parts in latex foam. Then, using hypoallergenic glue, line the orthosis with a soft polyurethane. All that's left to do now is buff the orthosis. This smooths all the surfaces. To ensure the orthosis delivers the goods, the patient redoes the key test while wearing it. Remember that scan showing red areas? They're gone now because the patient's feet now bear her body weight equally. This patient has arrived with a doctor's prescription for a knee brace. The orthotist analyzes his mobility, flexion, and balance, then sends the technical specifications to the production department. There, technicians make a model of the leg. They begin by positioning the leg at a 12-degree angle and wrapping it in plaster bandages. While waiting for the fast-set plaster to harden, the patient chooses a decorative pattern for the outside of the brace. The hardened cast serves as a mold. Technicians pour in plaster, let it harden, then remove the cast. After smoothing the surface, they draw technical markings, then install the lightweight aluminum joints that'll enable the orthosis to bend. Now they run a sheet of plastic through an oven. This is high-memory plastic, meaning that when you form it, it remembers the shape and maintains it. The design the patient chose comes printed on transfer paper. They use a laser thermometer to ensure the plastic is at the perfect temperature for the pigments to penetrate properly. They carefully position the hot decorative plastic on the model. Using a vacuum bag, they remove the air and press the plastic on tightly. The plastic sets in about 2 minutes, maintaining the form. They cut the required shape, line the inside, and sand the edges smooth. Finally, they attach straps to fasten the orthoses to the leg. The orthotist checks the fit on the patient, then runs various tests to make sure the orthosis is doing exactly what it's designed to do. Ever wonder how ballerinas manage to dance on the tips of their toes? It takes years of training, remarkable skill, and special ballet slippers. These toe shoes are handmade in what's truly a manufacturing pas de deux, a graceful pairing of traditional methods and modern materials. They sew the toe shoe's exterior from 3 pieces of satin. They cut those pieces using a press equipped with a metal die. It slices through enough fabric at a time to make 4 pairs of shoes. They also cut a pure cotton lining for each piece to protect the dancer's feet from irritation. This V-shaped piece is called the vamp. It'll become the front half of the shoe. The seamstress extends the V by attaching the 2 other satin pieces called the quarter panels. They'll form the back half of the shoe. She sews the ends of the V together, making a heel seam, which she reinforces with a rayon ribbon. Then she feeds the same type of ribbon through a special machine that folds it in half over a drawstring. She stitches it to the top perimeter of the shoe. This encased drawstring will enable the dancer to pull the shoe tightly around her foot. Now they put the satin upper onto a wooden form to check the sizing. It's absolutely critical that the height of the vamp be correct to within 3 millimeters. If it's even slightly off, the top of the shoe will cut into the dancer's foot. The shoemaker nails the cotton lining to an insole on the bottom of the form. The insole is made of rigid cardboard for support, imbued with plastic for flexibility. After trimming off the excess, he glues the lining onto the insole, making neat little pleats. Once the glue dries, he removes the nail and trims the excess pleating to eliminate any bumps that would irritate the foot. Now they sculpt the toe box, the hard encasing inside the tip of the shoe. It's made of papier-mâché, only instead of paper and paste, they use fabric and paste. Then they soften up a piece of resin-coated cotton in water and apply it on top. Next, they saturate 2 pieces of burlap with paste and apply them one after the other over the cotton. The paste is made of flour, water, starches, and a rubber and plastic-based resin that hardens to a semi-flexible state. That's key because the toe box has to be stiff enough to bear the dancer's full weight, yet flexible enough so that the ballerina can move fluidly. Now the final layer of fabric, a piece of pure cotton. They wrap the toe box in plastic wrap to keep the hammer clean as they square off the front, creating what's known as the platform. Then they press the toe box onto a piece of marble to make it completely flat. They verify that the platform is perfectly square. If not, the ballerina will topple over. After letting the toe box dry for 24 hours, they glue the lining over it with contact cement. They trim off the excess, then glue the satin over the lining, forming delicate pleats. They use lighter glue this time because contact cement would stain the fabric. They apply a foam filler to even out the shoe's underside, then coat it with high-strength vinyl glue. They apply the same glue to a sole, then leave both to air dry. 24 hours later, they put them on a heater set to 93 degrees Celsius. This reactivates the dried glue in about half a minute. They apply the sole, then put the shoe in a press for 15 seconds to solidify the bond. Now they can remove the shoe from the form. The sole is made of suede, a material that has just the right amount of grip. It's non-slip, yet still enables the dancer to glide smoothly across the floor. The last step is to glue in a white suede sock liner. It cushions the ballerina's foot and keeps it from slipping forward when she's dancing on her toes. A city's fleet of public transit vehicles might include standard buses, low-floor buses, or both. Low-floor buses have a special kneeling feature. When they pull up to the bus stop, they can mechanically lower themselves to curb height to make boarding easier for children, senior citizens, and handicapped people. This low-floor bus is 12.2 meters long and can carry more than 80 passengers. To build the bus's internal structure, workers put stainless steel bars into a press. It applies between 80 and 100 tons of pressure, bending them to the required shape. Workers assemble the structural pieces on a support frame called an assembly jig. They use an electronic inspection arm to verify their work. Once they've assembled the roof structure and the side structures, they bring them together for welding. Everything goes on a rotating jig. It turns like a giant rotisserie, giving workers easy access to whatever part of the bus they need to weld. When the welding is finished, they turn the bus right side up. They put the structure on a dolly and release it from the jig so that they can move it down the production line. Meanwhile, the stainless steel structure for the floor of the bus takes shape. Once that's complete, it's back onto the rotating assembly jig to weld it to the rest of the structure. This bus factory uses stainless steel because it stands up well to corrosion. Transit systems need to keep these buses running full-time for up to 20 years. Less rusting means fewer expensive and time-consuming repairs. Workers now move the completed structure to another part of the factory where they spray the underframe and lower section with a black anti-abrasion coating. This protects against the noise and damage that stones and other road debris cause when they hit the bottom of the bus. Next, workers apply high-strength glue to the floor structure and lay down a subfloor. Then they drive in screws for reinforcement. Now they turn the bus upside down to install 4 tanks of compressed air under the roof. 3 are for the brake systems, the 4th for the doors and other mechanisms. Melamine sealing panels hide everything that's under the roof. Next, the engine's radiator goes in at the rear of the bus. Then workers turn the bus right side up again and lay down a waterproof vinyl floor covering that's specially designed to withstand heavy-duty transit use. They cover the sides and roof with fiberglass panels. To prevent corrosion, workers use glue rather than screws or rivets. Then they attach the fiberglass front of the bus to the rest. The bus's low-emission diesel engine arrives at the factory already assembled. Workers attach it to the transmission and drive shaft in the engine compartment. Buses without air conditioning have sliding windows that open widely. On air-conditioned buses, just a small top section opens. The upholstery on the molded fiberglass seats is a velour-like fabric woven onto a strong canvas, then glued onto a fiberglass insert. This construction makes it impossible for vandals to slash the seat with a knife. Workers install the driver's seat, the steering wheel, and all the controls, including the toggle switch that activates the kneeling feature. This bus also has a ramp for wheelchairs. A safety system locks the accelerator pedal and applies the brakes to prevent the bus from moving when the ramp or kneeling features are in operation. The finished bus undergoes a half-hour water infiltration test with all the systems running. This ensures there are no leaks. At every phase of production, the factory does a quality control inspection, checking everything from mechanical safety to finishings, right down to the tiniest of details.
Pre-ink stamps, guaranteed to leave a lasting impression. Cranberries, more than a turkey sidekick. Putting a high-tech spin on cotton yarn. And road signs, reflective directives. Paid, rush, approved are some of the terms routinely stamped onto documents. Professionals such as engineers have their official stamps too. For years, you had to dab the stamp on an ink pad for each impression. Nowadays, you can get stamps with the ink built right in. The process begins with a design that either the stamp company or its customer creates with standard graphics software. They print the stamp design onto paper using a high-quality laser printer, then place the printout under an imaging camera. They feed in a blank sheet of negative film. Then photograph the printout. 30 seconds later, out comes the negative. The design is light, the background dark. Now they can begin making the mold for the stamp. They apply the negative to a plate of light-sensitive polymer, a plastic-like material. Then they vacuum out the air to prevent defects in the mold. Then they expose the polymer plate to ultraviolet light for approximately 3 minutes. The UV penetrates through the light part of the negative, the stamp design, and hardens the polymer underneath. The rest of the polymer is shielded by the dark portions of the negative, so it doesn't change. A wash cycle then scrubs away this unhardened polymer, leaving behind a perfect mold in the shape of the stamp. Now they cover the mold with a sheet of synthetic resin called Bakelite and put it into a machine called a vulcanizer. The machine heats the Bakelite to 154 degrees Celsius, then forces it into the mold using 2 to 3 tons of pressure. After 4 minutes, the Bakelite stamp is ready. To be more productive, the factory actually molds several stamps at a time. Next comes the built-in ink. They screw the Bakelite stamps into what's called the pre-ink mold, then pour in a mixture of ink and gel. They cover the mold and vacuum out the air, a process that takes 12 minutes. The mold then goes into a heat press for 17 minutes. The press applies 2 tons of pressure to expel excess ink and heats the ink gel to 127 degrees Celsius, transforming it to roughly the consistency of a marshmallow. So it won't overcook, the mold goes onto a special cooling table for 12 minutes. Next, it's set out to cool for another 45 minutes, this time on newspapers, which soak up more excess ink. Finally, they wrap the mold in paper towels and newspapers and vacuum out the last drops of excess ink. Then they quickly seal the back of the stamp to lock the ink in. Now they can cut apart the individual stamps. They glue the stamps by hand onto the base of the stamp handles. Before they're shipped out to the customer, all the stamps undergo a quality control check to make sure they'll leave a lasting impression. Cranberries are one of just a handful of fruits that are native to North America. Before the Europeans arrived, the Indians used them for food and medicine. The cranberry vine is well suited to a harsher climate. It thrives in low temperatures and loves acidic soil that's scarce in nutrients. Cranberries are ripe for the picking in late September. At harvest time, farmers flood their fields to make the cranberries float to the surface. Then they use a machine called a beater. It generates underwater turbulence, pulling the berries off the vines. The beater is suspended from a mobile bridge that's computer-guided to systematically work its way through the entire field. The beater cuts a swath about 7 meters wide with each sweep. Workers move the floating cranberries to one corner of the field, where a pump transfers them to a waiting truck. Along the way, the berries get a preliminary rinsing to remove branches and leaves. At the factory, the truck unloads its cargo. The cranberries travel along a water canal and onto a conveyor belt, then through a cleaning station, where workers use brushes and water jets to get rid of any remaining leaves and branches. Then they dump the cranberries into large bins to be frozen for up to several months. To produce cranberry juice, they defrost the frozen berries in hot water, then mash them, skin, seeds and all, into a puree. They add special enzymes to break up the pectin molecules, making the puree less viscous and therefore easier to press. The press processes 8 tons of puree at a time. That's the weight of 1.5 elephants. It takes 3 to 4 pressing cycles to extract all the juice. The juice then goes through a sophisticated filtration system. The 216 filters remove any plant particles or bacteria larger than 1 micron. A micron is 1,000 times smaller than a millimeter. Then they evaporate the water until the juice is 10 times more concentrated. Cranberries not destined for juice go through a grading process. Undersized berries drop down through the holes of a giant sifter. The bigger cranberries move on to the grading table, where workers remove any that are substandard. An electronic sorter then scans the remaining cranberries for color, signaling an air gun to blow any reject berries off the production line. The rest move on to the packaging department or continue down the line to be dried. Cranberries destined for drying are automatically seeded, cut in half, and pressed, then soaked in a sugar and water solution to make them sweeter. The side-to-side motion of the conveyor belt spreads the berries thinly so that they'll dry evenly. The hot air dryer subjects them to temperatures varying from 30 to 80 degrees Celsius. After about 3 hours, the cranberries come out looking like this. As you sip your cranberry tea, ponder this. Cranberries are a source of potassium and vitamins A and C, and drinking cranberry juice can prevent and treat urinary tract infections. Twisting plant or animal fibers into yarn dates back to ancient times, when people fashioned primitive spindles out of sticks. Around 500 BC, the spinning wheel was born in India. Today's factories have fully automated spinning machines that work on the same principle as a spinning wheel. This is a 2-ply commercial yarn, the kind factories use to weave fabric for making jeans and tops. It's made from large bales of raw cotton. Cotton comes from a plant, so naturally some leaves and stems are mixed in with the cotton fibers. To remove them, the first machine passes over the bales and removes a 5mm layer of cotton, then sends it through a duct system to the blending and cleaning machine. That machine processes 500 kilograms of cotton per hour. The cotton comes out evenly blended and cleaner, but still not clean enough. So it goes into a second cleaning machine, which finishes the job. Now the cotton goes through what's called a carding machine. It has huge rollers with wire teeth. They comb out the tangled fibers and line them up in parallel rows. The machine also discards any fibers that are too short to process. Next stop, the coiler. This device takes the rows of fibers and forms them into a thick and loose first stage yarn called sliver. The slivers move on to the drawing machine. It lines them up 6 at a time and draws them out, stretching them to form a second stage yarn. Then a machine called a roving frame stretches this second stage yarn, strengthening it by thinning it out until it looks like this. This third stage yarn is called roving. Depending on the type of yarn they're making, it's anywhere from 3.5 to 16 times thinner than sliver. They now stretch the roving up to 30 times thinner, which strengthens it even more. The yarn is finally finished. Now they have to transfer the yarn from all these small spools onto huge industrial-sized cones, 20 spools to a cone. One transfer method uses the winding machine. It winds the yarn from the first spool onto the cone. Then it automatically takes the back end of that yarn and attaches it with a knot to the front end of yarn from the next spool. It winds it onto the cone, then attaches the back end to the front end from the next spool, and so on. As each spool empties, the machine automatically discards it. And while all that winding's going on, the machine's optical sensor, that white object you see crossing the screen, does a quality control check. If a portion of yarn doesn't meet specifications, the winding stops, the machine cuts off the offending portion, then reconnects the ends and resumes winding. This is air jet spinning, another method of making yarn from slivers and winding it onto giant spools known as tubes. A suction tube grabs the front end of one spool and connects it to the back end of the previous one, again with a tiny knot. Before fully automated machines like this were invented 50 years ago, all that knotting had to be done by hand. The thin finished yarn is 200 times lighter than the thick first stage yarn that came out of the carding machine. From start to finish, spinning this yarn has taken 48 hours. You might not have noticed, but road signs have undergone a subtle change in recent years thanks to advances in technology. Today's signs are more reflective than ever. You can actually read them in the dead of night, even when the only source of illumination is your car's headlights. The earliest road signs were crude. A stick in the ground or a heap of stones to mark a route. In the Roman Empire, stone posts were erected along roadsides at regular intervals, indicating the distance to Rome. Centuries later, stone marker systems gave way to wooden cross signs pointing in several directions at once. The international system of road signs we know today came out of the first International Road Congress held in 1908. The process of manufacturing a road sign starts with a computer. The government strictly regulates the specifics of the design and requires a certain degree of reflectivity. The computer's specialized software guides a machine to cut the design on a sheet of film. Once the design is cut, workers carefully peel off and discard the pieces. What's left is a film stencil of the sign, in this case, a French stop sign. They inspect it for defects, then prepare a screen of polyester fabric that they'll later use to print the sign. They start by coating it with a thin layer of light-sensitive emulsion. Once the emulsion's dry, they adhere the film stencil, using vacuum pressure to flatten it and get rid of any creases or air bubbles. Then they expose the screen to an intense 6,000-watt light for 7 minutes. This activates the emulsion on the lettering and area outside the octagon, what's not shielded from the light by the film stencil. This exposed emulsion hardens, plugging the minute holes between the screen's fibers. After rinsing, you see the result. Elsewhere in the factory, meanwhile, workers cut the aluminum panels on which the signs will be printed. Using a punch press, they round out the edges and make holes for the bolts that'll later attach the sign to the post. They stamp on the company name and the year of manufacture for warranty purposes. They immerse the panels in a chemical bath to remove grease and other residues. Then they rinse off the panels and dip them in an acid solution that seals the metal to make it better withstand harsh weather. Next, they laminate the aluminum panels with a film containing minuscule glass particles. This film will make the sign reflect in the dark when light hits it. Then they cut the panel to the final shape. Now they can finally print the sign. The process they use is called silk screening, although the fabric screen, as you saw earlier, isn't actually silk, it's polyester. The machine forces the ink down through the screen onto the panel. The ink penetrates through the open fiber holes of the octagon, printing the red background of the stop sign. But it can't penetrate through the blocked fiber holes of the lettering and area outside the octagon, so those remain white. The freshly printed signs pass through a dryer at 66 degrees Celsius for 5 minutes. To produce street signs, workers first laminate aluminum panels with reflective film for the background color. Then either silk screen the street name or apply self-adhesive reflective lettering. But it's back to the silk screening process for printing multicolored signs. Workers print them one color at a time with a drying cycle between colors. All the film stencils are carefully stored for future use. The printed signs go into an oven for a final curing at 176 degrees Celsius, an hour for a one-color sign, a half hour per color for a multicolored sign. The ink is transparent enough not to block the reflective film underneath. Therefore, the entire sign, not just the lettering, is highly reflective. That maximizes the sign's visibility, thereby minimizing the excuses drivers can come up with for not heeding it.